Hi, everyone. Welcome to our next thrilling installment of CHY 113 lecture. Last time we began our look at thermochemistry, which is an investigation of the energy that's involved in various chemical processes, either physical or chemical. And so without further ado then, let's go ahead and look at our warm-up problems, covering what we did talk about last time. So in this first question, you want to calculate the heat lost by a sample of iron as it cools down. So go ahead and pause the video and try it out. See what you can do. Hopefully you got an answer of negative 5.63 kilojoules. And so I won't go through this one, but just remember that if you did miss it, we use our basic workhorse heat equation, Q equals mc delta T. If you got the sign wrong, then make sure you're looking at a couple things. One, delta T, your change in temperature is always your final temperature minus your initial. So it should have been 24.2 minus 99.8, resulting in a negative number for your temperature change, which gives us a negative number for our energy. And so that means that this is an exothermic reaction. Negative heats are exothermic, which makes sense. Remember, exothermic is that the system is losing energy, and this iron is clearly losing energy because it's cooling down. In this next one, we're adding energy into a sample of water, and you want to find the final temperature of the water given the temperature the water started at. Pause the video, try it out. Hopefully you got 45.9 degrees C. Let's actually work through this one. And so we use our same equation. We're going to use our Q equals mc delta T equation. We're given an energy, and we're given the mass, and we're given C, and we're given an initial temperature. So what we want to do here is solve for the change in temperature. Because if we find that, we can use that with the initial temperature to find the final. And so we're going to plug this in. And we also have to remember that C is given in joules. So we have to convert the Q we were given to joules. So that was 25 kilojoules. So we're going to have 25,000 joules divided by our mass, which was how much? 250 grams. And 4.184 joules per gram degree C for the specific heat of water. So we do this, we plug this into our calculator, 25,000 divided by 250 divided by 4.184, and we get a delta T of 23.9 degrees C. Now we have to remember though, that is delta T that we found. So if you found an answer 23.9, you just didn't carry it the rest of the way through. What we're solving for here is our change in temperature. And so we're going to go ahead and use that to figure out our final temperature. So remember, delta T is our final temperature minus our initial temperature. We're looking for our final temperature here. So our final temperature is going to be delta T plus our initial temperature. Delta T, we just solved for, 23.9 degrees C. Our initial temperature was 22.0 degrees C, giving us our final temperature of 45.9 degrees Celsius. In our last problem, we have an unknown sample of metal, so we don't know what this metal is. We heat it up, we drop it into some water, and when we drop it into water, the two of them eventually reach a thermal equilibrium and stabilize temperature. And so we want to find out the identity of this metal. So we went through problems just like this in the last lecture. And so to give you the hint, what you need to do here is find the specific heat of the metal and then use the table to identify what the metal is. So go ahead and pause the video now. See what you can do. Okay, and so rather than show you the answer right away, let's just work through this. And so remember that the basic principle here is that the metal's dropping down into the water. So the metal's going to cool down. And so we can calculate the heat lost by the metal, or the way that we would calculate that heat lost by the metal. Or sorry, I'll even back up further. We can represent the heat lost by the metal by saying negative Q. So negative Q, the metal's losing heat, it's losing energy, negative sign. Q being just our symbol for heat. Remember, that is going to be equal and opposite to the amount of heat that the water gains. Law of conservation of energy tells us that energy can't be created or destroyed. And so the amount of heat that the metal loses is equal and opposite to the amount of heat that the water gains. And so we can then set up our MC delta T expressions. And so negative mass of the metal times C of the metal times delta T of the metal, it's all going to be equal to the mass of the water times C of the water times our delta T of the water. So ultimately, we do need to be solving this for our C of the metal. This is what we're looking for. So a couple different approaches here. You could either just algebraically rewrite this equation to solve for C of the metal, and then plug in your numbers and go, or you could put in all of your numbers and then rewrite the equation after that. Either way. So I'm going to go ahead and just input my numbers here now. So our mass of the metal, we were given at 84.0 grams. C of the metal is what we're trying to solve for. Our delta T of the metal, our final temperature of 27.2 minus the 99.4. Our delta T of the metal is negative 72.2 degrees C. Our mass of the water at 250.0 grams. C of the water, 4.184. Our delta T of the water, 5.2 degrees C. And then we can just algebraically solve this for C of the metal. And so C of the metal, let's leave the units off for simplicity, show you what you would be inputting into the calculator. 250 times 4.184 times 5.2. We'll now divide that by negative 84 times negative 72.2. We put this into our calculator and we come up with an answer of, where did it go? 897. The units for this would be joules per gram degree C. And so that's the specific heat of this unknown metal. So we compare that to our table, and we see aluminum. Come on now, there we go. Aluminum. And so this is just using our idea of the law of conservation of matter, and in conjunction with our basic heat equation. And we just set the two of them equal to each other for the heat lost by the metal, heat gained by the water. Okay, so those are our warm-up questions from what we went over last time. So let's go ahead now and continue on with our discussion of thermochemistry. And so today we're going to pick up where we left off last time in talking about the energy changes that are associated with changing the states of matter. And then we're going to start looking a little, actually we've already been talking really about the first law of thermodynamics, meaning that energy is neither created or destroyed. That's sort of an interweaving thread through everything that we talk about here in this unit. And then we're going to move on to looking at chemical change or energy changes, which we're going to talk about enthalpy, but the energy changes associated with chemical reactions and how we can determine those energy changes. And the first method that we're going to look at for determining those energy changes is called calorimetry. And so let's go back and revisit changes of state. And so what we looked at last time was trying to find how much heat is absorbed as a certain sample of in this case, water, goes from -50 to 200 degrees C. And actually, let's back up and just remind ourselves what we're looking at here with our sort of our heat diagram. And so we talked about the fact that as something is warming up, or as we're just warming something up, the energy goes into warming that substance up until we reach the melting point. So if we're talking about a solid, until we reach the melting point, at which point all of the energy goes into actually changing the phase. So we're at 100% solid here. The energy is going into melting the ice until we're now at 100% liquid right here. Now that we're 100% liquid, the energy can once again go into warming the water up. So we're 100% water here, 100% liquid water, warmed up, still 100% liquid water here, until we get 100 to 100 degrees C. At the boiling point of water, now all the energy that we put in is going to go towards converting over to steam. Now at that point, we can start warming the steam up again. So the question that I left you with is basically, would it hurt more to be exposed to liquid water at 100 degrees C or steam at 100 degrees C? Neither one would be pleasant, but the steam at 100 degrees C is going to be a lot worse. It has a lot more heat. There's a lot more energy there. And so that's just another way that another thing to think about when we're looking at differentiating between temperature and heat. Things can be the identical temperature. Two different things can be the identical temperature, but one of them will have a lot more heat, a lot more energy involved. And so what we have to do then when we are looking at calculating the energy change associated with this entire process is we have to find all the individual energy changes. And so how do we find the energy change of each of these steps? Because they'll each be approached a little bit differently. And so as I was just showing on the graph, these are our basic steps. We first have to warm the ice up to 0 degrees C. We then have to melt the ice. We then heat the liquid water until it gets to 100 degrees C. Then we have to evaporate that water, change from a liquid to a gas phase. And then we heat up the steam. And so what we need to do is calculate the Q value for each of those steps and then just add them up. For some of the steps, actually, let me back up again. We'll just go all the way back through here. For our steps when we are warming something up, when we're warming our ice up to 0, when we're warming our liquid water from 0 to 100, and then when we're warming our steam up from, in this case, 100 to 200 is our target. In all of these phases where the temperature is actually changing, we're just going to use our old friend Q equals MC delta T. And we'll talk about that a little bit. The only thing that we do have to note is that the 4.184 figure that we've been using for C of water, that does only apply to liquid water. The specific heat of solid water and the specific heat of gaseous water are different. But it's our same basic equation, Q equals MC delta T. Now think about that for a second and think about if we can use that same Q equals MC delta T for these phases. Can we use that for melting? Can we use that for boiling? Hopefully you figured out, no, we can't, because there's a huge part missing. There's no delta T. Our temperature is not changing. And so we have to use something else in order to calculate the energy change associated with those changes of state. And so what we use are the heats of fusion and heats of vaporization. The heat of fusion is the amount of energy that's involved in converting a substance from solid to a liquid, or back the other way if we're losing energy. So it's the energy that's involved in transitioning between the solid and the liquid state. Likewise, the heat of vaporization is the heat that's transferred. It's the energy that's involved in converting a substance back and forth between the liquid and the gas state. And we have different figures for those. We have different numbers for those. Here's just a table with some typical heats of fusion and heats of vaporization. We can see here, for instance, that for water, it's going to take 333 joules for every gram of water that I have in order to convert it over into the liquid phase. And so if I have 1 gram of solid water at 0 degrees C, it's going to take 333 joules to then convert that over to liquid water. Likewise, if I have a gram of liquid water at 100 degrees C, it's going to take 2260 joules in order to convert that sample of liquid water over into a gas. And we denote these. So the delta H, the heat of fusion, the delta H of fusion versus the heat of vaporization, the delta H of vaporization. We're going to talk about this H in a little bit, but it's another of our indicators for energy. And so this table just sort of shows us the general patterns or some of the general heats of fusion, heats of vaporization. One thing to note, and this is something that we'll be returning to a little bit much later in the semester, but look at the difference in how much heat it takes to go from a solid to a liquid versus the heat it takes to go from a liquid to a gas. It takes a lot more energy. And this is on a per gram basis. So the same 1 gram of a substance takes you a lot more energy to convert that substance over to a gas as opposed to converting it to a liquid. And that has to do with the forces that hold particles together. And again, we'll talk about that much more when we get to talking about properties of gases, which is actually one of the last topics that we talk about in this course, so late April or so. But I just wanted to note it now, that it certainly takes a lot more energy to transfer something to the gas phase than it does to convert something into a liquid. And so let's look again at the steps that we would actually use for this. And so to warm the ice, so in this question, so we're looking at the heat involved to take 500 grams of water from -50 to 200. So at -50, we're at a solid phase where we've got ice, and we need to warm that up to the melting point. We need to warm that up to 0 degrees. So we're going to use our old friend, Q equals MC delta T. Now to actually melt that ice, now we're going to use Q equals our mass times the heat of fusion. And so times that 333. And those types of numbers will all be given to you. You don't have to memorize any of those. You probably do have 4.184 memorized at this point, just you've used it so much. But those types of numbers and heats of fusion, heats of vaporization, those will be given to you. So don't worry about that. Then our next step, so remember now we're at liquid water now at 0 degrees C. We're going to warm that liquid water up to 100. So there's Q equals MC delta T again. Now we're at liquid water at 100 degrees C. We need to convert that to steam. And so for that phase, it's going to be, our Q is going to be equal to our mass times the heat of vaporization. And then in our final phase, now we're going to heat the steam from 100 degrees to 200 degrees. There's Q equals MC delta T again. And like I said, just note that the C value is different for solids, liquids, and gases. So we do have to keep that in mind. And so we calculate it for each portion along the curve, and then we just add up our Q values. And so go ahead and see what you can do. Go ahead and try this problem and see what you can come up with for an answer. Here's all the values that you would need. And so remembering, certainly go back to the previous slide if you need to, go back to here, but use those two slides together to try to figure out the actual energy required for this process. And so pause the video now and try to do this calculation. Okay, hopefully you were able to come up with the answer. Let me just show you here what I've worked out for it. And so what I did here is just showed you the curve again as well, so you can see what's going on. And so here in 1, we're going from -50 degrees C to 0 degrees C. So we're going to use Q equals MC delta T using our correct C value, which was for solid water. And I just converted these to kilojoules as I went because the numbers you can see start to get pretty big. For 2, as we're melting the ice, we're using Q equals our mass times our heat of fusion. So there's the energy associated with that. Now we're going from, we're taking liquid water at 0 to liquid water at 100. So Q equals MC, the correct C value for liquid water, times delta T. And then our heat of vaporization here in 4, as we're going from liquid water to water in the gas phase. So our mass times our delta H of vaporization. And then finally, we heat the steam from 100 degrees C to 200 degrees C. So MC delta T gives us our value for the heat associated with that. We add them all up, and we get 1,650 kilojoules, rounded off for the appropriate number of significant figures. So hopefully you got something similar. Maybe a little difference in rounding somewhere, but as long as your process was the same, then you've got it. And so, as I mentioned, everything that we sort of do in this unit is kind of centered in around the law of the first law of thermodynamics. And so, like I said earlier, the first law of thermodynamics is not that you cannot talk about thermodynamics. I wonder how many of you actually get that joke. I'm curious. Email me if you understood that. Instead, the first law of thermodynamics is that energy can neither be created or destroyed. Actually, I'll do you one better. I'll see who's really paying attention to these lecture videos. So if anyone who emails me what I'm referencing when I say the first law of thermodynamics is that you cannot talk about thermodynamics, email me and tell me what I'm referencing there, and I'll give you 10 extra points on your next homework assignment. There we go. Little incentive. See who's watching the lectures. And so instead, the first law of thermodynamics is that energy can't be created or destroyed. Must either be, it's conserved and transferred in between the system and the surroundings. And actually, I'm not going to get into a lot of this. Your book goes into looking at the total energy of a system, and that the total energy of a system is the result of heat and any work that is done. And then goes into talking about the work done as pressure volume work, and the assumption that everything that we do as far as any sort of systems we're going to be looking at in this class are at a constant pressure. And all of that is just to finally get us to a point where we can say that the energy associated with what we're going to be looking at, 100% essentially of the energy associated with the processes we look at, is due to the transfer of heat. And so I'm going to gloss over some of that, what they were talking about in the book. I still want you to read through that. You still need to understand that. But just know that that entire discussion of pressure work or pressure volume work simply gets us to a point where we can make an assumption that all of the energy involved in our reactions, all the energy involved in the processes that we are looking at, is in the form of heat rather than heat plus work. That heat, the heat transfer and sort of the heat content of a chemical reaction is referred to as enthalpy. So when we talk about the enthalpy of a chemical reaction, what we're talking about is the energy transfer during a reaction. What's going on with the energy? That's what the enthalpy is. The symbol for enthalpy is H. And so when we say the H for a reaction is so-and-so, we're just referring to the enthalpy. Delta H is the change in enthalpy. So the change as we go maybe from reactants over to products. And as mentioned, at constant pressure, no work is done. That's the part that I'm sort of glossing over that is in your book. And so the heat flow, a measure of the heat of a system, is equal to Q, is equal to the heat that we've talked about, which is equal to these enthalpy changes. So again, really that's getting at the fact that all the energy change that we are concerned with is wrapped up in the enthalpy, is wrapped up in the heat energy of these different processes. And that's what we just talked about. And so one of the ways that we represent that, one of the ways that we represent the amount of heat involved in a chemical process is with what we call a thermochemical equation. And there's a couple different ways to express that. We actually normally don't express it the way that I have written here, but this is just, I wrote it like this to get us thinking about this, that in this particular reaction here, we're reacting carbon plus some oxygen to form CO2. We also see that in doing this, that energy 393.5 kilojoules is one of our products of this process. And so as carbon and oxygen come together to form CO2, energy is also liberated from that. Energy is released as a result of this process, meaning that this is an exothermic process, right? Energy being released by a system, energy being given away by a system is an exothermic process with a negative sign for heat. So in this case, it would be a negative delta H. And that's how we end up expressing a thermochemical equation. It's just like this. So we have our chemical equation, just like we've been looking at. But now, if we're concerned about the energetics of it, we're going to add in this delta H value. And in this case, this is an exothermic process. And so we represent our delta H value with a negative 333.5 kilojoules. And so that tells us that this process of bringing carbon and oxygen together to make carbon dioxide, that process releases 393.5 kilojoules of energy. Now this process and this enthalpy that we are given for the reaction, this enthalpy amount, is dependent on the stoichiometry as written. So in other words, when I look at this overall reaction, this means that the reaction of 1 mole of carbon with 1 mole of oxygen to produce 1 mole of CO2 is going to release this much energy. And so the enthalpy of a reaction is an extensive property. It does depend on how much is actually used. And so if I have 12 grams, assuming that carbon in this case is my limiting reactant, if I have 12 grams of carbon, that's about 1 mole of carbon, then I'm going to release the 393.5 kilojoules. If I only have 6 grams of carbon, however, that's half a mole. Half a mole is only going to release half as much energy. So half a mole would release about 196.8 kilojoules of energy. If I have a tenth of a mole, so if I'm told that I have 1/10 of a mole, 0.100 moles of carbon, that's going to release 1/10 of the energy, 39.4, 39.35. And so this is it's an extensive property, and it goes by the stoichiometry, which is very important for us. And so there's something else that we can, there's another way to look at these. What if we look at the reverse equation? What if we flip the equation around? If we look at CO2 plus energy gives us carbon and oxygen. So just the reverse of this equation. Now we see, looking at the reverse of this equation, now we have carbon dioxide plus energy. So energy is coming into this system now, making this an endothermic process. What did we talk about with the sign involved in an endothermic process? Sign is positive, right? And so energy is input, making it endothermic, which we would then write as this down below. Just trying to get my, oh, okay. And so our reverse process here, CO2 plus carbon plus oxygen, so it's just our reverse reaction. Now delta H equals positive the same amount of energy. And this is going to be something else that's very important for us to note as we move on in this unit, is that simply reversing a reaction, thinking about a reaction in the reverse direction, the enthalpy change is the same. The amount of energy, the magnitude of the amount of energy change is the same, but the sign is opposite. If a reaction written in one direction releases energy, then the reaction going in the opposite direction takes in energy. And that just should make intuitive sense, right? If something going one way releases energy, something going the other way is going to take energy. Think of it like biking down a hill. If I'm biking down a hill, that's releasing energy. If I'm biking back up the hill, that's going to take energy. Same sort of idea. Reversing a reaction, you reverse the sign of H, but the magnitude of it remains the same. And so overall, thermochemical equations represent the energy change that is associated with a chemical process. The sign of your delta H indicates that direction of energy flow. Negative sign tells us that the system, the reaction, is releasing energy. A positive delta H, indicating an endothermic process, tells us that the reaction has to take in an input of energy. These are extensive amounts. The actual amount of energy released or absorbed will depend on the amount of limiting reactant, just as the amount of maybe a precipitate formed. The actual amount of precip that is formed is dependent upon how much of the limiting reactant you have. So the amount of energy that is either released or absorbed depends on the amount of limiting reactant that we have. And the equation represents the number of moles in our balanced chemical equations. And so let's take a quick look at this one here, because one thing that I want you to recognize is that what a thermochemical equation does for us is it just gives us another set of, you guessed it, conversion factors, right? We look at this thermochemical equation and we can see that if I have 1 mole of N2, that's going to release negative 92.22 kilojoules of energy. If I have 3 moles of H2, that's going to release negative 92.22 kilojoules of energy. If I form 2 moles of NH3, that's going to release negative 92.22 kilojoules of energy. And you could use these conversion factors either way, depending, like any conversion factor, depending on what you are actually trying to solve for. So for instance, you might have a question that maybe tells you, oh, just to throw something out there. Let's say you're told that you have, I'll just make something up off the fly here. You have, or you create 56.2, you have a reaction which forms 56.2 grams of NH3. And we want to know how much energy was associated with that process. Same idea that we've done in other calculations involving stoichiometry, only here we're using our energy for our conversion factor. We know that for every 2 moles of NH3 that are produced, 92.22 kilojoules of energy are released. So our first step, we're going to take our 56.2 grams of NH3, and we're just going to convert that over to moles. NH3 is, what is 17.01, something like that. Nitrogen is 14.01, I think, isn't it? 0067. Plus our 3 times 1.008. Syntax error. Oh, there it is. 14.0067 plus 3 times 1.008. 17.03. So we're just converting over to moles of NH3. Then we're going to use our conversion factor, which tells us we release negative 92.22 kilojoules of energy for every 2 moles of NH3, directly from our thermochemical equation. So we put this into our calculator, 56.2 divided by 17.03 times negative 92.22 divided by 2. Tells us that this particular reaction would release 152 kilojoules of energy. So that's one of the ways that we use a thermochemical equation, is by calculating the actual amount of energy that would be absorbed or given off, depending on the equation, given some sort of amount that we work with. In this case, we were told how many grams of NH3 were formed and what's the energy associated with that. Now, to throw a little bit of a loop at you, remember how when we were balancing equations, and I told you that equations must always be balanced with whole numbers? Well, I'm going to mess with you now a little bit there. In thermochemical equations, it is actually okay to use fractional amounts. The reason for that is because sometimes we might be interested in the energy change. For instance, in our last equation, we might be interested for whatever reason in the energy change that produces 1 mole of NH3. And so we could rewrite our thermochemical equation accordingly. And if we do that, we have to also adjust the enthalpy. And so let's take a look at some examples. So this is the same thermochemical equation we just had. But in our first one, we want to write the equation for if we only form 1 mole of NH3. So if we only form 1 mole of NH3, that's going to just cut everything right in half. Right? That means that we're going to start with a half a mole of N2 plus 3 halves of H2. That's going to give us 1 mole of NH3. But now, since I've cut the whole thing in half, that cuts my enthalpy in half as well. So now my delta H is going to equal negative 46.11 kilojoules. You really should have been able to do that one in your head, Professor Staples. And so if we look at these others, the decomposition of 4 moles of NH3. So if we want a thermochemical equation that expresses that. So now we have to recognize 2 things. Now we have to recognize that we're looking at the decomposition of NH3, which is the reverse of this equation. And so the decomposition means the breakup of NH3. Not only that, we're looking at the breakup of 4 NH3. And so now that means that we have to double everything. If I break up 4 NH3s, that means that I'm breaking that into 2 N2s, and that would be 6 H2s, which means that 2 things are now going to happen to my delta H value, to my enthalpy. I've reversed the equations. That's going to reverse the sign. So now I'm going to have a positive energy associated with this. And I'm also multiplying this by 2. So our delta H is going to be 184.44 kilojoules now. Lastly, the combination of 1 mole of H2 with the stoichiometric quantity of nitrogen that would be needed. If I only have 1 mole of H2, then what I've done is cut everything down by a factor of 3. So I'm going to have 1/3 N2 plus 1 mole of H2 to create 2/3 of a mole of NH3. My delta H value, that one I definitely can't do in my head. 92.22 divided by 3. Can't forget my negative sign. Negative 30.74 kilojoules. And so in thermochemical equations, it is okay to have fractional coefficients. We're not looking at balancing. For when we're looking at this, we're not looking at the idea of balancing a chemical equation, coming up with our simplest whole number ratio. What we are looking at instead is real scenarios. We start with a regular balanced equation, just like this here. But then it just depends on what we want to look at. For whatever reason, we wanted to know in this first one, how much energy is liberated with just 1 NH3 being formed. And so we can change that. The reason we can do that is because keep in mind that what we're looking at now when we look at a balanced chemical equation is we're not looking at molecules. We're not looking at just 1 molecule of N2 plus 3 molecules of H2 gives us 2 molecules of NH3. We're no longer really looking at reactions in that way. We're scaling everything up and thinking in terms of moles. And so 1 mole of N2, 6.02 times 10 to the 23rd molecules of N2, plus 3 times 6.02 times 10 to the 23rd molecules of H2, give us 2 times 6.02 times 10 to the 23rd molecules of NH3. And so it's easy for us to think in terms of half of that, half of 6.02 times 10 to the 23rd, half of so and so, and so forth. And so we can think about things in terms of fractional coefficients when we are looking at thermochemical equations. And so finally today, we're going to start off looking at how we actually come up with thermochemical data. How do we find this? How do we know that the production of 2 moles of NH3 liberates 92.22 kilojoules? How do we actually get some of that data? We can measure it directly using a technique called calorimetry. If we can't measure it directly, then we can use other equations in what we call Hess's law, or we can also use what we call the heats of formation for products and reactants. Those last two will make up a good part of our next lecture. For the rest of today, we're going to look at this idea of calorimetry, how we can actually directly measure the energy associated with a chemical reaction. And so remember that or in general, we're looking at heat flow. And so with calorimetry, we're looking at just measuring that heat flow. And so think of it this way: if I have a calorimeter, which we can think of as pretty much a closed system. Actually, let me just go to the next slide. Here we go. This is a very simple calorimeter. 2 styrofoam cups nested together. It actually does create a very efficient environment. And so in those 2 styrofoam cups, I place a thermometer, or I put a thermometer in here to measure the temperature. Now just imagine this. Now imagine that I dump a reaction into this. I set a reaction going in the water. That reaction is going to either be endothermic or exothermic. And as that reaction progresses, the energy then is going to be transferred to the water or from the water. But we're going to have some sort of energy flow happening between the reaction and the water. We can measure the temperature change, whether or not the temperature is going up or down, endothermic or exothermic. And so we can measure that temperature change of the water. Now, here's the key part. Similar to when we looked at defining the specific heat of a metal, the law of conservation of energy tells us that the energy lost or gained by the reaction must be equal to the energy gained or lost by the water. And so we can measure that. We know the specific heat of water. So if we know the mass of the water that we had in our cups, it's easy for us to then calculate the energy either gained or lost by the water. And so let's just take a look at the equations involved with that. And so here we have, and I'll blow this up even a little bit. Here we have our calorimeter. There's our coffee cups. Here's our water in there. Here is our reaction, which just takes place in the water. Now, let's say we have an exothermic reaction. We have some sort of reaction where we're just taking A plus B, we react them together to form C, and delta H is something positive. Exothermic, I said. Delta H is negative. So it's an exothermic reaction. So the reaction is losing heat. The reaction is giving off energy. Where does that energy go? That energy goes into the water. And so what's going to happen to the temperature of the water? In this case, in this exothermic reaction, that means the water temp is going to go up. The energy is going from the reaction into the water. Water temperature is going to rise. Now, it's easy enough for us to measure the mass of the water. We know the C of water. We know the specific heat of water. And we can measure the delta T. So it's easy for us to calculate the Q of the water. How much heat did the water gain? And we know that the heat of the water must be equal and opposite to the heat of the reaction. Same thing would be the case if this were an endothermic process, if the reaction had to take in energy. And so if that occurs, then again, we've got our calorimeter here. We have our water. Our reaction occurs. Now we have, maybe it's just our reverse reaction. C makes A and B. So delta H is now going to be an endothermic process. So energy is going to come into the reaction. It's going to come in from the water. So the temperature of the water is going to go down. Same thing. We could then measure the heat of the water, Q equals mc delta T. We just measure the temperature change of the water. Is equal and opposite to the temperature change of our reaction. And that's calorimetry. We can't necessarily measure the output of the output or the input, but we can't measure the energy change of the reaction directly, but we can measure the effect of that energy change on the surroundings. And that's what we're doing. We're measuring how much energy change is associated with the water, because that must be equal and opposite to the energy change from the reaction itself. And so go ahead and try this one. So in this one here, we have 6.10 grams of sodium hydroxide dissolving in 100 grams of water. And we see that the temperature rises from 21.6 to 27.8. And so we want to calculate the delta H. We want to calculate our enthalpy for this solution process. Now, not only that, but we usually go a step further. That quite often with these sorts of processes, we want to know the kilojoules per mole of NaOH. And so when you calculate your kilojoules in the way that we just talked about, you then need to divide those kilojoules by how many moles of NaOH were even present to begin with. So go ahead and pause the video and see if you can find the energy change associated with this dissolution process. Okay, did you come up with something? Hope you did. Let's go ahead and work through it. And so we have our coffee cup calorimeter. And so what we're going to do is calculate the energy change associated with the water. So Q equals mc delta T, 100.0 grams of water, our specific heat of water, our water change was 16.2, positive 16.2 degrees C. So this gives us 6778 joules. We know we want our final answer in kilojoules. We might as well go ahead and round this off now. 6.78 kilojoules. Now we do want this in kilojoules per mole, as we were told 6.10 grams of NaOH. We convert that to moles. 1 mole of NaOH per 40.0 grams of NaOH, just our molar mass of sodium hydroxide, gives us 0.1525 moles. So we'll take our 6.78 kilojoules divided by 0.1525 moles, gives us 45.5 kilojoules per mole. Are we done? Is 45.5 our answer? Let's think about this just for a second. The 45.5 kilojoules per mole, that's the amount of energy the water gained. So that's the amount of energy associated with the water. That must be equal and opposite to the amount of energy that the reaction lost. And so that's our final answer, is delta H for the reaction is negative 44.5 kilojoules per mole. We could then write that into a thermochemical equation. We have our dissolution of sodium hydroxide solid, goes to sodium hydroxide aqueous. So all we're doing is taking solid sodium hydroxide and dissolving it. And we have our enthalpy information. Delta H equals negative 44.5 kilojoules. And this is written out in just terms of 1 mole. And so that works out for us. And so that's how we could go about finding, for any reaction. We could run any reaction in a coffee cup calorimeter and calculate the amount of energy change based upon the energy change of the water inside our calorimeter. Now, here's another example. So here we have some ammonium nitrate dissolving in water. Now the temperature drops from 22 to 16.9 degrees C. So go ahead and calculate the delta H for this process and write the resulting thermochemical equation. So pause the video now and see what you can come up with. Hopefully you came up with something like this. So there's our equation for ammonium nitrate dissolving, solid ammonium nitrate to aqueous ammonium nitrate. And our delta H value equals positive 25.8 kilojoules per mole. Let's just think if that sign makes sense. And so in this case, the temperature of the water is decreasing. That means that the system, the reaction, had to have gained that energy. And so that means that from the point of view of the system, from the point of view of the reaction, it was an endothermic process. It means it's a positive sign for delta H. Now, calorimeters like this, and sort of this idea of the nested coffee cups, works great for general chemistry labs or running some sort of educational lab, or even for some other industrial purposes, they can work okay. But when we want to get really exact with things, we use what we call a bomb calorimeter. Same exact idea. The whole idea behind the process is the exact same. It's just a much more technical setup where we have what we call the bomb, so the steel bomb where the actual sample goes in, and then a pretty sophisticated process here, a pretty sophisticated setup as far as the water and the temperature, something to stir the water to make sure the temperature stays constant throughout, and then some ignition wires to get the sample actually burning in there. But it's the same exact idea. It's the same exact process. This is just a more technical setup that enables us to control the environment a little bit more and to account for energy changes associated with the calorimeter itself. Because hopefully, something that a few of you thought of as we were talking about our coffee cup calorimeters is, in those examples, we're making the assumption that all of the energy from the reaction is being transferred directly to the water and that the coffee cups don't take in any of the energy. The reality is they are going to take in some. And the reality with this bomb calorimeter is that this bomb here is also going to take in some of the energy. And so this bomb that this whole sample is nested in is going to retain some energy too. And then the rest of the energy gets out to the water. So we also, if we're getting technical, really highly technical data like this, and this incidentally is how some food companies actually do find the nutritional content of their food. If you want to know how many calories your pork rind has, throw your pork rind into a bomb calorimeter and literally burn it and measure the resulting energy change. And so, like I said, though, the only difference in this big setup is that we're now also accounting for the energy that this steel bomb is going to absorb as well. And so for that, we also have, so our heat of the reaction is going to give off heat, which both the bomb and the water are going to absorb. And so we need to take that into account too. And so for questions like this, we also have to calculate the heat of the bomb. How much heat does the bomb itself take in? And to do that, all we do is we take the C of the bomb. We would know the specific heat of the bomb itself and multiply that by our temperature change. The temperature change of that bomb calorimeter is assumed to be equal to the temperature change of the water. So let's just look at how we would do that. And so here we have a sample of glucose that is placed into a bomb calorimeter, and we ignite it, and we have a resulting temperature change. And so far it looks pretty similar to everything that we've looked at so far, but we're also given the heat capacity of the bomb itself. So the heat capacity of the calorimeter, and we're going to take that into account too. So go ahead and pause the video, see if you can put together everything that we've talked about, try to come up with an answer. Come up with something? Hopefully you came up with negative 2814 kilojoules per mole. Let's take a look at this. And so, like we had mentioned, and so the law of conservation of energy tells us that the heat of the reaction plus the heat associated with the bomb plus the heat associated with the water, law of conservation of energy tells us that's going to be 0, which tells us that ultimately the heat of the reaction is going to be negative, the reverse of the energy associated with the bomb plus the water. And so we can find the heat associated with the bomb is just going to equal the heat capacity of the bomb that we were given of 847 joules per degree C times our temperature change of 11.7 degrees C, giving us 9,909 joules that the bomb absorbs. That's how much the actual bomb calorimeter, how much that bomb will absorb. But then we can also calculate the heat that the water absorbed by using our old friend, MC delta T. We had 850 grams of water, 4.184 joules per gram degree C, times our temperature change, gives us 41,610 joules. So we just add those up, and that's the overall heat given off by this reaction. Then we're just going to convert that over to kilojoules. So again, that was 51.5 kilojoules. That's given off, though, by 3.30, given off by, all right, that's just too messy even for me. So 51.5 kilojoules of energy given off by 3.30 grams of the glucose. We want to know the energy associated with 1 mole, though. So just like we just did with our last example, we're just going to convert from grams to moles. So 330 grams divided by our molar mass, 180.15, means that we have 0.0183 moles. So we're going to take our 51.5 kilojoules, divide that by 0.0183 moles, which then ultimately gave us our final answer of negative 2814 kilojoules. What I forgot to carry through with me, and that is going to bring me to a point that I'll talk about, but what did I forget to carry through? Forgot my negative sign up here, didn't I? Which meant that ultimately this was negative here for our kilojoules. And so, which brings me to my last point. This is all we're pretty much done for today, but I want to talk about the negative signs a little bit here. You'll see that it becomes very easy to forget about a negative or forget to carry one through. And I mean, I've been doing this for a long time. You saw how easy it was for me a couple times now to forget about my negative signs. That's why it's so important to think about your answers when you're done. So if I hadn't thought about this one when I was finished, if I had just left it and said, oh, 2814, okay, I'm done, I would have gotten this wrong. But instead I took a second to think and say, okay, well, 2814, but I know that this glucose combusted, this glucose burned, raising the temperature of the water. So this glucose had to have released energy. Releasing energy is an exothermic process, which must have a negative sign. And so it starts to become even more crucial in this thermochemistry unit to really just think about your answers for a second, and especially those signs and the direction of energy flow, and think about if it makes sense. Because like I said, as we see, it's very easy to lose track of those negative signs. But if you take that second to think about it at the end and think about, okay, what was my direction of energy flow in this problem? And what does that mean the sign of my answer has to be? Take those few seconds to think about that, and you'll save yourself a lot of what you what all of you call stupid mistakes on things like exams. Take those few seconds and think about the direction of energy flow. Because if you had submitted 2814 as an answer for this, it would be wrong. Thermochemical calculations are not correct unless both the magnitude and the sign are correct. And that's true in Chem 101. That would be true if I was giving live exams. If this were a normal semester and you were taking this test on paper, sitting in front of me in the huge lecture hall, if you simply wrote 2814, if you did all this work and you wrote 2814, I would mark that as 100% incorrect, no partial credit, because it is not correct. And so take those few extra seconds and think about the sign of your answer and whether or not that makes sense. And so that is it for today. We will wrap things up next time in talking about 2 other methods of finding thermochemical data. And so in the meantime, I sincerely hope that everybody has a great day.